Okay. So let's start giving some fundamental information about complex functions. In particular, we will deal with the so-called analytic functions of one complex variable. The fundamental property of analytic function is that of being differentiable. Differentiable will be defined in a moment, the meaning of this word, but we will see that this assumption of differentiability, in contrast to the case of real functions of one real variable, produces extraordinary consequences, even though the definition is exactly the same as for real variables. So, as you see in the box, if you have an open set of the complex plane omega, and if you pick a point z0 in this set, if you form the incremental ratio, so you divide f of z minus f of z0 by z minus z0, and you consider the limit of this ratio as the variable z tends to your point z0. Now, if this limit exists, we will denote this by f prime at the point z0, and we'll call this limit the derivative of the function f at the point z0. This tells us that the function is differentiable at this point, so nothing new with respect to the real case. Now, the power of complex differentiability, actually, and the difference with respect to the real case is that the limit we have just mentioned is now a limit to be performed in the metric of the plane. So we are moving in the complex plane, real axis, imaginary axis, and you should approach the point z0. You are free to approach the point z0 from any direction in this plane. This gives us all the power of differentiability in the complex plane. For instance, if you consider a function f and you explicitly indicate the real and imaginary parts of the variable z with the letters x and y, and also you split the real and imaginary parts of the function f and you call them respectively u and v, then you can, for example, choose to introduce a real increment. So you move parallel to the real axis of the complex plane. If you do that, your increment will be real, so you basically are performing a partial derivative with respect to x. So if you do this derivative on the function f, what you get is the partial derivative of u with respect to x plus j, the partial derivative of v with respect to x. And this is one possible form for the derivative, for the complex derivative of the function f. However, an alternative possibility is to give instead an imaginary increment to the z variable. In this case, so the denominator of the incremental ratio is purely imaginary, and it's equal to j times the increment along y, which is the vertical or imaginary axis. So in this case, you get 1 over j is our letter for the imaginary unit, times the partial derivative of the function f with respect to y, which means, equivalently, minus j, the derivative of u with respect to y, plus the derivative of v with respect to y. Now, this is an alternative expression for the same thing. So you can equate those two expressions and they must be equal. And if as you know, if two complex quantities are equal, this means that their real parts are equal and also their imaginary parts are equal. This gives you immediately this system of real equations, which tells you that the derivative with respect to x of u is equal to the derivative with respect to y of v, and vice versa. The derivative with respect to y of u is equal to the derivative of v with respect to x, with a change of sign in this second relation. Okay? This set of relations is very important, and it has also a name. This set is called the Cauchy-Riemann equations. And what we have showed is actually the simplest part of the following theorem, which is fundamental, the so-called theorem of Luhmann and Menchoff, which tells you that if you consider an open set, again, omega, and a continuous function f in omega, and this function has partial derivatives with respect to x and y, almost everywhere, which means everywhere but in a at most countable set in omega, then the function f of z is holomorphic in omega, which means is analytic, if and only if it satisfies in omega the Cauchy-Riemann equations that we have obtained in the previous slide. So the Cauchy-Riemann equations in turn imply differentiability if you assume that your function is continuous and has partial derivatives almost everywhere. Now we can define the class of holomorphic or analytic functions. The word holomorphic is the same as analytic. If the derivative of the function f exists for any point z0 in the set, in the open set omega, we will say that f is holomorphic or analytic in this set omega, and we indicate the class of all holomorphic functions defined in the same set omega with the symbol h of omega, where h, of course, stands for holomorphic. And it's easy to check that if you have two holomorphic functions, f and g, then also their sum as well as their product is holomorphic in the same domain, so that technically, from an algebraic point of view, the set of holomorphic function in omega is a ring. And also, you can apply the usual differentiation rules for those holomorphic functions. In addition, you can also make superpositions of holomorphic functions. So if f is a holomorphic function defined in omega, and the image set of omega is contained inside another open set omega 1, where another holomorphic function g is defined, then you can superpose the functions f and g. So you go from omega to omega 1 through the function f, and then from omega 1 to some another set in the complex plane through the function g. What you do is to obtain a third function, let's call it h, and technically this is written in this way, g o f. Then this new function h is again holomorphic in omega, and you can calculate its derivative using the usual chain rule. So the derivative of the function h is simply the product of the derivatives of the composing functions f and g. Okay. By simply applying these considerations, you will discover easily that, for example, any monomial z to the nth power, where n is an arbitrary integer, positive integer, is a holomorphic function, and it is holomorphic in the entire plane, in the entire complex plane. Now, when a function is holomorphic in the entire complex plane, the function itself is called an entire function. And since monomials are entire functions, the same will be true for any polynomial in Z, which is just a linear combination of monomials. So polynomials are the standard example of entire holomorphic functions. Also, the rational function 1 over z is holomorphic. However, you should exclude the origin, of course, where this function is not defined. So if you take as the composing function g in the previous slide, the function g of w, which is equal to 1 over w in the chain rule, and if you consider any arbitrary holomorphic function f1, f2, and again, if f2 has no zero in omega 1, then you will see easily that the ratio of those two holomorphic functions, f1 divided by f2, is holomorphic in omega 1. So what you obtain is that, for example, applying these two polynomials, if you make ratios of polynomials, and so you get a rational function, this rational function will be a holomorphic function in the set of the complex plane that excludes all the zeros of the denominator. Okay, so this is an example of a function which is holomorphic, but not everywhere. That's because, as you all know, any polynomial has at least one zero, and actually it has a number of zeros which is equal to the number to its degree. Now, these are very elementary examples, polynomials and rational functions, but it's possible to obtain much more variety. And the basic idea to obtain this variety is to use power series, which is the generalization of polynomials to infinite orders of monomials. Okay. First of all, let us recall some basic property about power series. To each power series, where you can see here now you have an index n which goes from 0 to infinity, you have coefficients cn, and there is the nth power of the increment z minus a. Well, to each power series of this kind, there corresponds a unique number, r, which may be equal to 0 or larger than 0, and can also be equal to infinite, such that the series converges absolutely and uniformly in any disk D with center A and radius r for every r which is less than capital R. So if the radius of the disk is strictly less than this capital R number, then you have guaranteed the convergence of the series, which is also absolute and uniform in the closed disk. The fact that the disk is closed is indicated with this over bar. On the other hand, you know also that the series diverges if Z does not belong to this closed disk. So if you are outside the disk, the series diverges. This number r is known as the radius of convergence, and you can calculate it, for example, using the root test. So the reciprocal of the radius of convergence is the superior limit, when n tends to infinity, of the nth root of the absolute value of the coefficient Cn. Now, note that we cannot say much in advance about the behavior of the power series when you are exactly on the circle of convergence, so when the distance from the point 8 is equal to r. Actually, what we can say is that there will be at least a point on this circle where the series does not converge. But in general, any behavior is possible. So it's possible that the series converges everywhere on the circle, but for a single point. And also it is possible that the series does not converge anywhere on this circle, so we have a natural boundary, and any other behavior in between. Let me give you an elementary example of a power series, which is very important, the geometric series, in which you have those simple monomials, z to the nth power. And in this case, the initial point is the origin of the complex plane. All the coefficients are equal to 1. So if you apply the root test, you discover that the radius of convergence is equal to 1. This means that the geometric series converges absolutely for any z whose absolute value is less than 1. And actually, you know well the sum of the series. It can be given in a closed form. It's the rational function 1 divided by 1 minus z, which is an example of a holomorphic function inside the unit circle of the complex plane. This is holomorphic in the interior of the circle, and actually it is holomorphic everywhere with the exception of the point where z is equal to 1, which is the 0 of the denominator. Note that the geometric series is not convergent outside this circle, so outside the green area, even though its sum is a holomorphic function also outside the circle. For example, you could manipulate the sum 1 divided by 1 minus z to show that it is actually possible to represent the same function as a different power series, having as initial point any arbitrary number z0 different from 1, as you can see in the plot, in the drawing here at the bottom. Take an arbitrary z0, and if you manipulate the denominator by adding and subtracting z0 from the denominator, and then you factor out the factor 1 minus z0, what you end up is this ratio here in red, which you can recognize is the sum of a geometric series whose term is here expressed as the ratio between z minus z0 and 1 minus z0. So we have a representation of the function f inside a new circle whose center is equal to z0 and whose radius is equal to 1 minus z0 in absolute value. So basically, you see that what limits the circle of convergence is the presence of this point 1, where the sum of the series is not holomorphic, and actually it has a singularity, and we will see that this is a pole singularities in the next lesson. So it is possible to obtain many different series which represent the same function in different disks. So we are ready to give a definition. A function f defined in omega, which is always an open set of the complex plane, is said to be representable by power series in omega if to every disk contained in omega there corresponds a series, which in general is different from any disk, which converges to your function f of z for all the points z inside the disk. And the theorem, the fundamental theorem, is that if a function f is representable by power series in omega, then f is holomorphic in omega. So by means of power series, we have the possibility of defining holomorphic functions. But in addition to that, the first derivative of the function f is also a function representable by power series. And to obtain its representation, what you need to do is to just differentiate term by term the series. So what you get is what you see here at the bottom. The first derivative, f prime of z, is equal to this series where now n goes from 1 to infinity. That's because you have explicitly this n factor inside. So it's pointless to start with 0 because that would give you no contribution, okay? And now you can see there is the coefficient Cn and also the n minus 1th power of the quantity z minus a. Two remarks about this. Since the first derivative now satisfies the same hypothesis as f does, so it is a function which is representable by power series, you can go on and apply the same theorem to the first derivative. So if you do that, you will discover that the second derivative exists and it is representable by power series, and as a consequence, the third derivative exists, and so on. So you will discover that the function f has derivatives of all orders, and all are representable by power series, and each derivative can be obtained by differentiating term by term the right number of times the original power series. And because of this, we come to the second remark, it is possible to discover that the general coefficient of any power series is related to the corresponding derivative of the function f of the sum of the power series evaluated at the initial point a. And there is also this factorial term here that pops up because of the calculations that you can see above. So you can understand that this means that the coefficients of a power series are uniquely determined for each point a, for each initial point a in omega, and therefore each power series in the complex plane is actually the Taylor series of its sum. As you know, the Taylor series has as coefficients the derivatives divided by the corresponding factorials. So what we are saying is that any power series is actually a Taylor series, okay? And now another fundamental example of a holomorphic function, in this case a holomorphic function that is defined by means of a power series, which is the exponential function, and this is probably the most important function in mathematics. It is an entire function, so this is holomorphic in the entire complex plane, and that's defined by the infinite series given in the box above. As you can check easily, the radius of convergence is infinite, and that's why the exponential is an entire function. And this means that the series converges absolutely everywhere, and the absolute convergence allows us for evaluating the product of two of those sums by rearranging the terms, because when a series converges absolutely, you can apply the associative property. And if you do that with some smart tricks from combinatorial analysis, you will discover that the product of two exponentials, so the exponential of a, say, times the exponential of b, is equal to the exponential of the sum a plus b, which is the well-known addition formula for the exponential function. Also from the power series, you will see immediately that the exponential function evaluated at the origin is equal to 1. And now we introduce a shorthand notation by letting e be equal to the exponential function evaluated at the point 1. We will write the exponential function as e to z. So z is the power to which that we give to the number e to represent the exponential function. And as an exercise, a very useful exercise to be done at home, you can try to prove that all the following properties of the exponential function hold. First, for every complex number, the exponential function is different from 0. Second, the exponential is equal to its own derivative. That's probably the simplest among those. Third, the restriction of the exponential function to the real axis is a monotonically increasing positive function, which tends to infinity when x tends to positive infinity and tends to 0 when x tends to minus infinity. So those are the well-known asymptotic behaviors of the real exponential. Four, there exists a positive number, let's call it pi, such that if you calculate e to j times pi over 2, that's equal to the imaginary unit j, whereas e to z is equal to 1 if and only if z is an integer multiple of 2 pi j. Of course, pi is the usual quantity that we call pi, so 3.1, 4, etc. 5, the exponential is a periodic function of its argument, and the period is purely imaginary, and it's equal to 2 pi j. 6, the map from the real axis and the real variable t to e to jt, that's a map of the real axis onto the unit circle. So this means that any point of the unit circle is reached by this map. So it comes from some point of the real axis. And finally, 7, if w is a complex number which is different from 0, then there exists some complex number z such that w is equal to the exponential evaluated at the point z. Okay, that's an exercise for you. The last of those properties actually gives me the occasion to introduce the logarithm, which is the inverse function of the exponential. By definition, z is equal to the logarithm of w if z is a root of the equation w is equal to the exponential of z. And first of all, since, as we say, the exponential function is never equal to 0, then the number 0 has no logarithm. For any number different from 0, then if you set the equation w is equal to the exponential of x plus jy, and you split the exponential in the product of two exponential, the first factor is the exponential of x, and that's equal to the absolute value of w, whereas the second factor is an exponential with a purely imaginary exponent, e to jy, that's equal to the ratio between w and its absolute value. Now, the first equation, the one involving x, has the unique solution x is equal to the real logarithm of the absolute value of w. That's the logarithm in the real domain. Whereas one of the previous properties in the previous slide tells us that the second equation, the one involving y, has a unique solution, which is between 0 included and 2 pi, and it is also satisfied by any y that differs from this solution by an integer multiple of 2 pi. Okay, that's because the exponential is a periodic function. So any non-zero complex number has infinitely many logarithms in the complex plane, and those infinite logarithms differ from each other by some multiple of the quantity 2 pi j. And the logarithm allows us also to define the argument of a complex number w. That's because the logarithm can be written by splitting the real and imaginary parts as the logarithm of the absolute value of w plus an imaginary part that by definition is the argument of w. And as you of course know, this is nothing but the angle between the segment from the origin to the complex number z and the positive real axis in the so-called polar representation of complex numbers, which is an alternative to the Cartesian representation in terms of real and imaginary parts. Okay, so in a compact notation, we can write any complex number z as the product of its absolute value, let's call it r, times an exponential with a purely imaginary exponent, where theta is the argument of the complex number z. Of course, the argument as the logarithm is defined up to multiples of the quantity 2 pi. as any angle is. Having defined the exponential, we can define the cosine and sine functions in terms of the exponential. This is a link which is not apparent at all in the real domain, whereas it is very clear in the complex domain, the link between the trigonometric functions and the exponential functions. You can check that by adopting those definitions, you obtain trigonometric functions whose power series representation is exactly the ordinary power series that defines the trigonometric functions for real arguments. Furthermore, you have the Euler's identity. The exponential is equal to the cosine plus j sine, and that's true for any complex number z. Then you have the fundamental trigonometric identity, so the sum of the squares of the cosine and sine functions for any z is equal to 1. And finally, the derivative of the cosine is equal to minus sine, and vice versa, the derivative of the sine function is equal to the cosine. All the other trigonometric functions, like the tangent, cotangent, etc., can be defined in the usual way in terms of the sine and cosine functions, and all of them can be seen to be rational functions of the exponential, of the complex exponential e to jz. Also, the inverse trigonometric functions can be defined easily once you recognize the link between the trigonometric functions and the exponential. This requires the inversion of the exponential. So the inverse, for example, the inverse cosine is given by this representation in the box, where you can see there is a logarithm and a double sign. And the inverse sine function can be obtained in a similar way, or maybe more easily directly in terms of the inverse cosine function by taking into account the property of complementary angles. As you can see, so in the theory of complex analytic functions, basically all the elementary transcendental functions, so trigonometric functions, the exponential, the logarithm, they are all related to the exponential. So there is essentially only one elementary transcendental function, which is the complex exponential function. Okay. Now, in terms of using the complex exponential, we can also define the general power of a complex number. So if you have two complex numbers, a and b, then you define a to the bth power as the exponential of b times the logarithm of a. And since the logarithm in general has infinitely many values, also the power a to b in general has infinitely many values, and all those values differ by a factor which is e to 2 pi j and b, where n is an arbitrary relative integer number. Actually, it is possible that there is only a single value of the power, but that's possible if and only if the complex number b is actually a real number, and even more if it is an integer number n, and in that case that's an ordinary power, like in monomials. Okay. Or also it could be also a negative integer, like in rational functions, so a or a to minus 1 are examples. If you have instead a rational number as the exponent of your power, then in that case you have a finite number of values, and in particular it's easy to check that you have exactly q values if q is the denominator of the reduced form rational representation of the exponent b. So if your exponent b is cast in the form p over q, where p and q are natural numbers, and if this is a reduced fraction, then your power will have exactly q values, and those can be represented as a root. So a qth root, that's not a square root, but a qth root, that's a typo. And those q order roots actually are placed along a circle in a complex plane. They are equispaced along the circle. For example, if you take the number j, the imaginary unit, and you calculate the power of j to the ratio 1 over 4, so what you do is to calculate the fourth root of j, and this means that you have to take the argument of j, which is pi over 2, and divide it by 4, and that gives you pi over 8, but also you can add any multiple of pi over 4 and you obtain all the other points. So in total you have 4 points on this circle that give you the 4 possible values for the fourth order roots of the quantity j. So what you get is basically a polygon in the complex plane whose vertices are the roots of qth order in general. Okay, the last part of this lesson is devoted to analytic functions as mappings, but I think this is a good moment to make a short break. So it's 11. Maybe we can start over in say 10 minutes. So see you in 10 minutes. If there are any questions so far, again, please ask me. I'm sure that everything I've said so far is very well known to you, but I thought it would be useful anyway to reintroduce basic material just to have the foundations for what we will say from now on. Okay, see you in 10 minutes then. Okay, here I am back. Let me enlarge again the screen and we can start over. Okay, in the last part of this lesson, I will tell you something about analytic functions when they're viewed as mappings from one complex plane to another complex plane. To set some foundation, let us first examine some consequences of the Cauchy-Riemann equations that we mentioned before. First of all, we have, as we saw the possibility of expressing in different ways the derivative of f at any point z inside the domain of analyticity. For example, one possibility is to use real increments, and therefore you can see there are the partial derivatives with respect to x. Alternatively, you can use purely imaginary increments, and in this case you have the partial derivatives with respect to y. But in addition to that, by using the Cauchy-Riemann equations, you can also relate the derivatives with respect to x of one function to the derivative with respect to y of the other function. And so you can mix the partial derivatives, for example, in this way, the partial derivative of u with respect to x minus j, the partial derivative of u with respect to y. So in this case, you have only the u function. Or alternatively, you can employ only the v function, and in this case you have the partial derivative of v with respect to y plus j, the partial derivative of v with respect to x. So 4 possibilities, which can be more convenient or less, depending on the case. For example, you can calculate the squared absolute value of the derivative, which is the sum of the squares of the two partial derivatives of u with respect to x and of v with respect to x. But this is also equal by the Cauchy-Riemann equations to this quantity, the difference between the products of these partial derivatives, u with respect to x, v with respect to y, minus u with respect to x, and v with y, times v with respect to x. And now you can recognize that this difference of products is nothing but the determinant of the so-called Jacobian matrix of the functions u and v with respect to the variables x and y. As you may recall, the Jacobian matrix is a matrix in which you consider a certain number of functions of a certain number of variables, and you calculate all the possible derivatives of all the functions with respect to all the variables. In this case, we have 2 functions and 2 variables, so you have a 2 by 2 matrix whose determinant is the Jacobian determinant. Now, in the next lesson, on the basis of the complex integration, we will establish the fundamental fact that the derivative of an analytic function is itself an analytic function. So by this fact, its real and imaginary parts, so the functions u and v, will have continuous partial derivatives of all orders. And hence, by the Schwarz theorem, their mixed derivatives will be equal. So we can conclude that the Laplacian of the real part u, as well as the Laplacian of the imaginary part v of any analytic function, that is the sum of their second partial derivatives, that's equal to 0 in any domain of analyticity. We say this synthetically by saying that u and v are harmonic functions. That's because u and v are solutions of the Laplace equation. That's the Laplacian of u is equal to 0 and Laplacian of v is equal to 0. And solutions of the homogeneous Laplace equation are, by definition, harmonic functions. Since those functions u and v are not only harmonic functions, but they are also the real and imaginary parts of the same analytic function, then they are said to be harmonic conjugate of the other. And actually, if you are given one of them, you can recover the other up to an additive constant. So basically, you need to know only one of them. Now, let us, having said this, we can examine the behavior of an analytic function as a mapping. And in particular, you can consider the analytic function f as a mapping between a complex plane with real and imaginary parts x and y to another complex plane with real and imaginary parts u and v. For example, you can consider an arbitrary smooth curve, gamma, drawn in the first complex plane, so the plane of the z variable, and you can ask what is the image of this curve in the second complex plane. Let's call this image gamma prime. Now, any smooth curve is represented by a map from a parameter t to, in this case, the complex plane, for example, the complex plane of the z variable. So you have a map z of the real variable t, where t is a parameter which belongs to a certain interval. Now, the image of gamma, so gamma prime, is by definition the composition of the holomorphic function f and the parametric representation z of t. So you end up with a parametric representation in which the second complex plane, let's call this complex plane the plane of the w variable, contains another smooth curve w in which t is again the parameter of the curve. For example, you can calculate the length of the original curve gamma, and by definition the length of the curve gamma is given by an integral from a to b, which are the endpoints of the interval to which the parameter t belongs. The integrand being the square root of the sum of the squares of the first derivatives of x and y with respect to the parameter t. This is by definition from differential geometry. This can also be written synthetically using complex functions as the integral of the absolute value of the first derivative of the z function as a function of the parameter t. Now, conversely, the length of the image, for the same reason, will be the integral from a to b of the absolute value of the first derivative of the w function of the same parameter t. But now, this derivative, w prime, can be evaluated by using the chain rule, because w is the composition of the function f and the function z. So you have the product of the first derivative of the function f evaluated at z and the first derivative of the function z. The absolute value of the product is, of course, the product of the absolute values. So you end up with this expression in red here for the length of gamma prime, which tells you what is the meaning of the absolute value of your holomorphic map, so of the absolute value of the first derivative of the function f of z. The meaning is that this quantity provides you the scaling factor for the elementary lengths, because as you can see, in addition to the differential with respect to the parameter t in the last integral, you also have this absolute value of f prime of z, which gives you the elementary length of gamma prime. Okay, so in general, lengths are not preserved by the map, but they are changed, and they change according to this scaling factor, the absolute value of the derivative of the map. Okay, we can also consider areas. In this case, you consider, for example, a set E, a measurable set of the complex plane Z, and its image under the analytic map F, which we will call E prime. Okay, the area of the set E is by definition the integral with respect to x and y of the constant of the unit constant. Okay, whereas the area of E prime is by definition the same integral with respect to x and y to u and v, but you can calculate the integral with respect to the original variable x and y by applying the usual rule for changing variables in integrals with respect to more than one variable. And the rule tells you that the differential must be changed, and there is the Jacobian determinant that gives you the scaling factor for the elementary areas. Now, this Jacobian determinant, as we observed a few slides ago, is actually the square absolute value of the first derivative of the map. So in this case, you have this additional interpretation for the derivative of the map, its squared absolute value gives you the scaling factor for elementary areas. Okay, whereas the absolute value is the scaling factor for lengths, the squared absolute value of f prime gives you the scaling factor for areas. But there is even more. Let's come back to curves, and now let us consider a pair of curves in the z-plane. Let's call them gamma 1, this one here, for example, and gamma 2, and consider their intersection point. Let's call it z0, okay? The tangent vectors at that point to the two curves will generally be different, and there will be an angle theta between those tangent vectors. Tangent vectors, of course, are nothing but the derivatives of z with respect to the parameter once calculated for gamma 1 and once calculated for gamma 2. Now, if you consider the map and then the images of those curves, you will end in the W plane with a pair of curves, let's call them gamma 1 prime and gamma 2 prime, which will be intersecting in the image of z0. And at that image, again, you can calculate the tangent vectors. Now, since, again, by the chain rule, the derivative of w with respect to the parameter t, so w prime of t, is equal to the product of the first derivative of the analytic map f times the derivative of z with respect to the parameter. If you consider the argument of this equality, since the argument of a product is the sum of the arguments, you will discover that the argument of the derivative w prime evaluated at t0, which is the parameter that corresponds to the intersection point z0, well, this argument is equal to the sum of the arguments of the function f prime evaluated at the intersection point z0 plus the argument of z prime evaluated at the parameter t0. This means, in considering that the argument of a complex number has the meaning of an angle, this means that basically the angles are modified in the same way. So basically you add to all angles the same quantity, which is the argument of the first derivative. And since this is true, this means that the angles formed by those tangents to the curves will remain unchanged. The tangents themselves will be rotated in the plane, but they will be rotated of the same quantity, so their mutual angle theta will be conserved. So when two curves which form a certain angle at their intersection point are mapped upon curves that form always the same angle, then the mapping is said to be a conformal mapping. Okay, and this conformality will hold at any point where the first derivative of the map is different from 0, exactly for the reason that you can see in this slide. So, for example, if you consider in the complex plane x and y, let's say horizontal curves that intersect vertical curves, so horizontal lines, straight lines that intersect vertical straight lines, these set of curves have their mutual intersection, which form angles equal to pi over 2. They will be mapped in the W plane in generally not straight line, but curves. However, the mutual angles between the tangent of those image curves will be again pi over 2. And here you can see some example. For example, here, unfortunately, the images are a bit blurred, but in the top left image, you can see, for example, the function f defined by 1 over z, and you can see, for example, in blue and red, the images of the straight horizontal and vertical lines, which, as you can see, intersect each other at right angles, so with a mutual angle equal to pi over 2. And the same is true for all the other examples. You can see z squared over 2, 1 over 2 z squared, the square root of z, for example, and so on. Here you can see the exponential map, in which you can see that the horizontal lines, so the lines where the imaginary part is constant, they are mapped onto circles having constant radius, the red circles here, whereas the vertical lines, so the points where the real part of z is constant, they are mapped instead. Sorry, the vertical lines are mapped on circle. The horizontal lines are mapped on the radial lines in blue. Okay, but again, those two sets of curves intersect the right angles. Okay, and the same is true for the sine function, the cosine function, and so on. Now we can ask ourselves if a given map, a given analytic map, is invertible. That's an important question to ask. And we will see that the essential condition for having invertibility is that the first derivative is different from zero. In fact, if you have an analytic function defined in omega, and the mapping that this function establishes from omega to some omega prime is known in advance to be one-to-one, that is a bijective mapping. That is not always the case, but if you know that this is the case, and also you know that the inverse is continuous, so the inverse exists and it is continuous, then the inverse map is also an analytic function. That's easy to establish because under these assumptions, it is easy to see that the first derivative, f prime of z, is different from zero everywhere in omega, and therefore you can calculate the derivative of the inverse function. And as you know from the elementary calculus, the derivative of the inverse function is nothing but the reciprocal of the derivative of the direct function. So it's equal to 1 over f prime. So that's why it's important that f prime is different from 0. You need to calculate this ratio, and so therefore the denominator must be different from 0. But let us try to make the inverse assumption. So now, conversely, let us assume that the first derivative, f prime, is different from 0 at a given point, z0. What can we deduce from this fact? Well, this allows for concluding that the mapping established by the function f is bijective, so it is one-to-one, and it has a continuous inverse. However, we can conclude that this is true only in some neighborhood of the point z0. So what we are guaranteed is that there is a neighborhood of the point z0 at which the derivative is different from 0, so that in this neighborhood, or in shorthand locally, the inverse map exists, is bijective, and with continuous inverse. And of course, the inverse map is also analytic. And this is easy also to establish, that basically because, as we observed, the squared absolute value of the first derivative, f prime, that's equal to the Jacobian determinant. Now, if the Jacobian determinant is different from 0 at any point, you can enforce the implicit function theorem, that in Italy is called the Dini theorem about inverse functions, which guarantees you that locally the inverse function exists. So again, locally means that this is true in some neighborhood of z0. Can we go from local to global? Well, in general, no. Because even if the first derivative of your function, of your map, were different from 0 in the entire open set omega where the function is defined, then we cannot in general assert that the mapping is bijective with a continuous inverse in the whole region, that is globally. So the fact that the first derivative is different from 0 does not guarantee that there is an inverse function, so that the mapping is one-to-one, and in addition that this inverse function is continuous from one region to the other, and that this holds globally. So why this is true? So why this cannot be asserted in general? Well, in intuitive terms, what may happen is depicted in this figure, in which on the left you can see the domain omega, the open set omega, which is represented as the union of two of its subsets, omega 1 and omega 2, represented respectively with cyan and green colors. And then there is the map, represented by the red arrow, that gives you the images omega 1 prime and omega 2 prime. So it is possible, for example, that the mapping from omega 1 to omega 1 prime is 1 to 1. And it is also possible that simultaneously the mapping from omega 2 to omega 2 prime is also 1 to 1. The problem is that the images, omega prime 1 and omega prime 2, they may overlap. And in the overlap region, therefore, it is not possible to go back in only one way to the original points, because in the intersection between omega 1 prime and omega 2 prime, you are both, by definition, simultaneously in the two regions. So you can go back either to omega 1 or to omega 2. So there is not a one-to-one inverse map. As you can see in this drawing, what I have done is to represent things as if the whole region in which the omega region is mapped were made of a transparent film which partly cover itself. So with this idea in mind, you can understand quite easily what Riemann had in mind when he first introduced the concept of a Riemann surface that we will now, about which we will now say something. Let us give some examples. The simplest example of all is provided by the polynomial z to the second power, so z squared. And this gives you the simplest possible example of a Riemann surface. More generally, we could, with the same approach, examine the Riemann surface of any monomial z to the nth power, where n is an integer greater than 1. For example, in the case n equal 2, if you adopt a polar representation of the complex number z, so r, the absolute value, and theta, its argument, by squaring, you end up with a complex number w, whose absolute value is r squared, so it's the absolute value of z squared, whereas the argument is the argument of z doubled. That's because here you can see in the exponent we have 2 times theta. So all the arguments are doubled. So consider, for example, the cyan region here of the z-plane, in which the argument theta goes from 0 to pi. So we are in the upper half plane of the complex z-plane. Since theta goes from 0 to pi, when you square the complex variable z, the angles will be doubled, and therefore we will go from 0 to 2 pi. So in the complex W plane that you can see depicted on the right, you cover the entire plane, because theta now goes from 0 to 2 pi, so you make the entire tour from the positive real u-axis to the negative real u-axis, okay? Of course, along the positive u-axis, you have an ambiguity, because you could come back either onto the positive reals x or to the negative real x, so you have to choose. And to indicate that here you have an ambiguity, we draw this wiggly line in which you can imagine that the W plane has been cut, like if it were made of a sheet of paper, and you take scissors and you cut the paper from infinity to the origin along this wiggly line, so to avoid that this wiggly line is crossed. But if you consider now the green region, in which you see that we are now in the bottom half plane of the z-complex plane, and therefore the argument theta goes from pi to 2 pi, by squaring, so going into the W plane, something very similar occurs, because by doubling the arguments, then we go from 2 pi to 4 pi. And now going from 2 pi to 4 pi is exactly the same then as going from 0 to 2 pi. So we again cover the entire W plane with the exception of this wiggly line. Okay, so any of those regions, the cyan one and the green one, is mapped onto the entire W plane. So by definition, when this happens, a region is called a fundamental region. So the cyan region is a fundamental region, and the green one as well. Okay, the mappings, note, are one-to-one. Okay, however, of course, the images of the cyan region and the green region are completely overlapped, because they are two copies of the same W complex plane. Okay, of course, then if you decide to come back, so to define the square root function, in order to take the square root of the number w, then you have to take the square root of the absolute value, which is a positive real number, and then you have to divide by 2 the argument. However, the argument being defined up to multiples of the quantity 2 pi, this means that the argument of the square root will be defined up to multiples of pi. And this gives you the well-known fact that there are 2 possible square roots of the same complex number. That is because basically you can come back from W to Z by choosing to land onto the cyan region, and so with arguments between 0 and pi, or to land back on the green region, so with arguments from pi to 2 pi. This corresponds to choosing this number n in the formula above as an even number, and in that case you go to the cyan region, or as an odd number, and in that case you go to the green region. The wiggly line, by the way, is known in complex analysis as a branch cut. That is because it allows you to define a single valued branch of the function, in this case the square root function. Of course, in this case you have in total 2 possible branches, okay? And here, of course, there is nothing special in the real positive axis. You can draw any line from the origin to infinity in the W plane, and this would define equally well a branch cut. For example, you can choose the negative U axis, and this corresponds to having 2 different fundamental regions. In this case, the regions are the left and right half planes of the original Z plane, okay? But any line going from 0 to infinity in the W plane would do the same. The important point is to be aware of the choice and to be coherent with the choice in all the calculations. Now, here you can see a pictorial representation of the Riemann surface associated with the square root function, which by itself is a 2-valued function. However, considering what we have said so far, it can be also considered as a 1-valued function. However, its domain must be doubled. So instead of considering the argument of the square root as belonging to a single complex plane, you should consider 2 copies of the complex plane, the upper copy and the lower copy that are known technically as Riemann Sheets. So we talk of an upper Riemann sheet, the upper plane, and the lower Riemann sheet, the lower plane. So each of those planes are cut along a branch cut. For example, in this case, you could consider the negative real axis in both planes. And those 2 copies of the complex planes are glued together so that when you cross the branch cut, you go from one sheet to the other. And the closeness of points in the same sheet and between different sheets is indicated in this figure by the use of similar colors. So, for example, if you consider the upper sheet and you go from the purple region by describing a circle to the red region, then we go into the yellow, finally into the green, and then you see if you cross the branch cut remaining on the upper sheet, there will be a discontinuity in color. However, if you go instead on the bottom Riemann sheet, then you go from green to green, so this indicates continuity. That's because if you do that, you maintain continuity of the branch of the square root. So you continue your tour in the bottom sheet again, following a circular path from the green to blue to dark blue, and finally you cross again the branch cut in the lower Riemann sheet and you pop up again to the upper sheet. That's difficult to visualize because the topology is not something that could be achieved in our ordinary 3-dimensional space. This kind of connection is not easy to achieve, but you can imagine this kind of connection. Actually, the whole mathematical branch of topology originated from Riemann surfaces, because those are non-trivial examples of surfaces which are different, essentially different from the ordinary surfaces that we can see around us. Okay, but here in this case, apart from geometrical considerations, the main point is that if you have a multi-valued function like the square root, in this case a two-valued function, you can make it single-valued if you accept that its domain is not a simple complex plane, but it's something more complicated. In general, a complex surface, the Riemann surface associated to the function, that in the square root case is made of two copies of the complex plane glued as I tried to describe you before. Okay? Another consideration is that the point, the origin, so the starting point of the branch cut is a special point because it connects all the copies of the complex plane. So if you see those two copies of the complex plane, the two Riemann sheets, you should imagine that they are glued together at the origin, and that the origin is a common point because between those two copies. That's because the origin is the only place where the square root function has only one determination, or more exactly, its two determinations collapse into a double one, okay? In this case, the initial point of the branch cut is called a branch point, and more generally, a branch point need not connect all sheets. There could be more than two sheets, and some branch points could belong to only a subset of those. If it connects h of those sheets, then we say that it is a branch point of order h minus 1. So in the example of the square root function, the branch point connects two sheets, and therefore it's a first order branch point. But for example, if you consider the cubic roots, in those cases there are three sheets and the origin would be a second order branch point, and so on. Let us examine a related example, which is again associated with the square root function. In this case, the function is given by w equal to the square root of z0 squared minus z squared, which you can imagine to obtain by a composition of functions, the simple square root function of z prime, and then there is z prime, the intermediate variable, which is equal to z0 squared minus z squared. If you examine first the function w equal to the square root of z prime, then you could, for example, choose the positive real axis of the z prime complex plane as a branch cut. You see the red wiggly line indicated here explicitly, the branch cut. The real part of z prime is greater than or equal to 0, whereas the imaginary part is equal to 0. And the branch point is the origin. Now, this branch point is mapped into a pair of points, plus and minus z0, as you can see from here. If you go from z prime to z, so from the plane of z prime to the plane of z, the origin of the z prime plane is mapped into a pair of points, because the square root of z0 squared gives you two possible determinations that are equal to plus z0 or minus z0. Okay, those two will therefore be branch points for our function here on top. And in particular, the branch cut along the positive real axis is mapped to a pair of hyperbolic branch cuts, as you can see here in the bottom figure, where you can see the wiggly lines again are the branch cuts, and they run along those two hyperbolas in red. To obtain this, it's very simple. You just write down the relation between z prime and z explicitly by separating real and imaginary parts. If you do that both in z0, in these brackets, and in z, and you separate now the real and imaginary parts of z prime, then the branch cut, this branch cut in z prime, for which the real part of z prime is greater than or equal to 0 and the imaginary part is equal to 0, becomes this system of equations, x0 squared minus epsilon 0 squared minus x squared plus y squared greater than or equal to 0, which is an inequality, and defines therefore a region of the complex plane, which is the region between those two dashed green hyperbolas. And then there is an equality that comes from the imaginary part of z prime equal to 0, that is x0 y0 minus xy equal to 0. And this is, you can recognize in this equation, the equation of an equilateral hyperbola, which is made of two branches, one in the second quadrant and the other in the fourth quadrant of the Cartesian plane, or the complex plane. And so therefore, by putting all the pieces together, you discover that the wiggly lines that are parts of those equilateral hyperbolas are the branch cuts pertaining to our square root of z0 squared minus z squared. Take in mind these particular examples because in a few weeks we will find an important use of this particular example of branch cuts, which are known as Sommerfeld branch cuts in the analysis of waves in planarly layered media. Finally, we can consider the exponential function. The exponential function is a single-valued function. However, it is a periodic function, as we mentioned before the break of this lesson, and the periodicity runs along the along the vertical imaginary axis. So, if the exponential z equal to e to w is represented here, you can see on the left the W plane in which each colored region is a fundamental region. That's because the map, the exponential map, takes any of those regions onto the entire z-plane with the exception of a branch cut, which is conventionally chosen to run along the negative real axis. So we have a branch point, 0, and a branch cut along the negative real axis. This means that if you consider now the inverse function, which is the logarithm, you have the possibility of going back from the z-plane to the w-plane in infinitely many ways. Each way corresponds to the choice of a different fundamental region. And this is made explicit in the expression of the logarithm, in which you see the real part of the logarithm is fixed, and it's given by the logarithm of the absolute value of the argument of the logarithm, in this case r, whereas the imaginary part is not uniquely defined because it's given up to multiples of 2 pi. So you see here you have an integer n, which can take any value, positive, negative, equal, and also 0, okay? Of course, when you deal with the logarithm, in order to make the calculations consistent, you should choose only one of those determinations, and typically the choice is the one that here is represented with the cyan region. So the argument of the logarithm goes from minus pi to plus pi, and this is the so-called principal branch of the logarithm, okay, that corresponds to this choice of the branch cut. And here you can see an image that gives you an idea of what would be the shape of the Riemann surface associated with the exponential function, with the logarithm, sorry. Since the logarithm has infinitely many valued, the Riemann surface will be made of infinitely many copies of the complex plane. They are joined to each other by means of the branch cuts that run along the negative real axis. So if you make a tour, for example, from the bottom of this figure around the origin, and you go from the negative real axis again to the negative real axis, then you will end up in the second, in the upper Riemann sheet. So you don't come back to the purple region, but you go onto the red region. And if you do the same again, you climb the stairs and you go to the next Riemann sheet, and so on. That's an infinite number of sheets, so you never come back. Whereas in the square root example, if you do your circular tour twice, you come back to the starting point. In the case of the logarithm, this is not true, because that's an infinite stair, like Jacob's stairs that joins heavens to earth, if you wish. So this is an example of a Riemann surface that is made of infinite Riemann sheets, and in which, by the way, there is a branch point, which is the origin, which, differently from the square root example, does not belong to any of those sheets. That's because the origin of the complex plane is the only point of the complex plane which is not reached by the exponential map. The exponential function takes any value that could be shown rigorously, with the exception of the value 0. So the origin is an example of a branch point that does not belong to the Riemann surface. As an exercise, you can study, for example, the inverse cosine function, which is related to the exponential and to the logarithm, or better, to the logarithm function. And you could try to prove that those represented here on the left are the fundamental region for the inverse cosine function, and that the branch that correspond to the choice of the branch cuts indicated on the right. There are a pair of wiggly lines that join the point -1 on the real negative axis to -infinity, and the other one joins the +1 point on the positive real axis to +infinity. If you cross any of those lines, you change Riemann sheet, and there are also in this case an infinite number of Riemann sheets. That is because the inverse cosine function is defined in terms of a logarithm function, and so for the same reason as the logarithm has an infinite number of sheets. That's also a useful exercise for you, in addition to the exercise about the exponential function that I showed you in the first part of this lesson. Okay, I hope that at least parts of this material was not covered by your previous courses, so I have said something new. Of course, this is only the shortest possible introduction to this matter. I will go on in the next lesson to introduce complex integration. But of course, the subject of complex analysis is very, very vast, and it is covered in a number of beautiful books. Among those that I know, I can advise you to read the classical book by Lars Valerian Halford's Complex Analysis, which is an old book. It appeared in the 50s of the last century, and then it was reprinted. It's available in a pocket edition. It's not too expensive, and it's really well done. Another beautiful book is the one by Rudin that's more tough to study, Real and Complex Analysis, that covers in the first 10 chapters real analysis, advanced real analysis, so measure theory, integration, Fourier transforms, and so on. And in the second part of the book, there is complex analysis. That's tougher, I would say, more synthetic, but it's also beautiful and very rewarding, especially if you try to do the exercises. And finally, there is a more modern book by Conway, Functions of One Complex Variable, which is a standard textbook, very complete, very didactical, so it's also advisable. I think that for today it's I'm done. So I thank you for your attention, and if you have any question about this stuff or any other thing, please ask. Otherwise, I will stop here. Just to make a little survey, was this material already familiar to you or not? If anyone wants to activate his microphone, assuming you are still there.
For me, no.
It was the first time.
Yes, not all, but
Okay.
Also for me, it was the first time. Yes.
Okay, well, that's good news. Of course, I invite you to deepen the subject by reading those books or any other standard textbook on the argument, which is really beautiful. And okay, same for me. I'm reading the chat, some things, but not all. Okay. Perfect. I will make the slides available to you in a short time. I've run into a few typos. Maybe you also noticed some. So if you write me by email about some errors, I will be grateful to you. And I will also make the recording available on the e-learning website of the course as soon as possible.
Sorry, I have
Yes.
an issue.
Yes.
I cannot enter as a guest to the course on e-learning.
Okay, then I will try to do that for you by using your email, and then I will ask you by email if you can enter. So be prepared to receive an email from me in which I ask you to check.
Okay, thank you very much.
Okay, the same I see for Andri, so I will do that for both, and then you can tell me if that worked or not. Okay. So thank you for now for having been present today. See you Thursday, same hour. I hope I will be able to deliver the lesson also in presence, if any one of you wants to be present in the second floor of the department. Also thanks to Fabrizio Frezza for attending this course, this lesson, and see you the day after tomorrow.
Thank you. Have a
Bye
nice
bye.
day.
Bye-bye.
Thank you very much.
Bye.
Bye-bye.
Bye.
Thank you. Bye.
Bye bye.